Okay, as we're waiting, today is the last day of notes. So we have one section we're going to go through. So you'll see that a lot of the stuff afterwards, we're just not going to do. We just picked out those two sections. The other thing that'll be a little bit different than what was on the schedule is I'm going to modify a little bit how we're going to do the test for this unit. Originally, we were going to have the test on Monday, similar to how we had done the test before, but I'm going to change that for a couple reasons. One is because we're not really doing a homework quiz first, you don't really have a chance to practice stuff before you have to take it on the test. And I'm still putting test grades in, everything's still weighted like it was. The other reason I'm going to change a little bit is because you guys also are going to start going into videotape your graduation walk on Monday. So that would kind of disrupt that, having that set time like we usually do for the test. So what we're going to do for the test for this unit, we're basically going to make it a giant homework quiz. So it's going to be a 50-point homework quiz, which, like I said before, is basically 25 points on titrations, 25 points on solubility. It may end up being not that big, but that would be the biggest it would be. And then we'll take it just like we would a homework quiz. It'll go in the grade book as a homework quiz. That way, if this week's time wasn't enough to completely grasp everything, that won't lower your grade. A big deal if you miss a couple. You can still work on it with partners, again, because we're doing this whole thing in a week. I want to make sure this is fair because we have to cover the stuff, but I don't want it to negatively affect your grade if we haven't spent enough time on it. So Monday, we'll still take the test or quiz, whatever you want to think of it as, the final assessment for this unit. And it'll be set up like a homework quiz. So it'll be a window over the course of the day. So like in the morning after we review until like 8 o'clock at night. So that should give you plenty of time to get that done depending on other things you have to do that day. Okay, does that sound good?
Yep.
Okay, so what we're going to look at today is the last section that we're going to cover. And can we all see our screen here?
Yep.
Okay, so this is talking about solubility equilibrium. So this is the last K. These are the last ice tables that we'll have to use. They're similar to the other ice tables. They can just be a little more confusing because there are coefficients in most of these, where when we've done ice tables before, there haven't been coefficients. So what we're talking about when we're talking about solubility, first of all, solubility is how much of a substance will dissolve in a given amount of solution. Now, the weird thing about these is that most of these things we're talking about when we talk about solubility are things that before we would have considered insoluble. So when we talked about solubility before, if you remember back in the first semester, there were some things that would dissolve, some things that didn't, and we had those solubility rules that we used. So what this is looking at is most of these things that we look at are things that don't dissolve, or we would have classified as insoluble before, but everything has some degree of solubility, even if it's just a little tiny bit. So what this KSP value tells us is it represents the dissolution of an ionic compound. So when you're starting with these, you're still going to set these up like a dissociation. So the same way we set up a dissociation of like a strong acid, a weak acid, all of those other dissociations that we set up. And then when you set up the K for it, the K is still products over reactants raised to the power of the coefficient. So if you look at the KSP for this one, it's just Ca plus 2, and F minus raised to the second power because of that coefficient. This is not included because all of these, that initial substance is a solid. So when you set the KSPs up, it's only going to be the products, because if you remember before, the rules of setting up a K is you don't include pure solids and pure liquids. So calcium ions, this is an aqueous substance, this would be an aqueous substance, so that's why those are included. That's why we don't include that initial substance. So that's going to hold true for all of these KSPs that we set up. The biggest thing you have to be careful of with these is, because we didn't really have to deal with these before, are these coefficients. So these are going to it's going to take a little bit of time to get used to dealing with those in the ice tables and other things. So you have to make sure that you raise that to the power of the coefficient if there's a coefficient there. Okay, so when we're talking about solubility, the way that these two things are related is that, like we said a second ago, solubility means that it's the amount of a compound that will dissolve in a certain amount of solvent at a given temperature. So most of the time when you look up solubility in the back of the book, and a lot of solubility charts that we look at are going to be given in grams per like 100 milliliters of water. That's usually a kind of a standard way of showing solubility. What we're going to focus on is looking at something called molar solubility. So molar solubility is looking at how many moles of a substance would dissolve in 1 liter of solution. Now, if we had more time, we would bring back in the solubility in grams. But like I said, because we're covering this super quick in a week, we're just going to focus on kind of the highlights of it. And we're going to focus on molar solubility when we're talking about this. So in the back of the book, just with the rest of the K values that you looked at, there are also KSP values. So let's think for just a second, just to kind of get a context of what we're talking about here. When we look at a solubility, when something dissolves, let's start there. So when something dissolves, let's pick something like, let's just look at this first one here. So BAF2. For this to dissolve, if you put this into a solution, those two substances would have to dissociate from each other to dissolve. So that's dissolving means those two things kind of break apart. So what the KSP tells us, if you remember what that value is, because it's products over reactants raised to the power of the coefficient, it tells you to what degree those particles dissociate. So when we talk about most of these things as what we would classify as insoluble, look at how small these values are. So these are really, really, like, look at that one, -36. So that means a very, very, very small amount of those ions are actually dissociating. So that's kind of relating back to when we said most of these things we would consider insoluble. It's because it's a very small amount of them actually dissociates from most of the things that we're talking about. Okay, so the calculations that you do with these, there's going to be two main types of calculations. One is going to ask you to solve for molar solubility or give the solubility of the ions in the solution. The other type of calculation you have to do is going to ask you to solve for the KSP given the molar solubility. So just like when we did values with ice tables or calculations with ice tables and Ks before, they either have to give you the K if you're solving for molar solubility, or they have to give you the molar solubility if you're solving for K. So that's kind of how you would be able to tell the difference between these. So on this first one, it says calculate the molar solubility of lead chloride in water, lead 2 chloride. So what you would have to be given here, you could go to your table and look this up. The KSP is 1.17 times 10 to the -5th. Okay, Ks again, those don't have units just like before. So when we're doing this, the biggest thing to remember, and this will kind of help keep things straight, is anytime they say molar solubility you can think of as X. So when we set up our ice table, the X in the ice table is our molar solubility. If they want the molar solubility of the compound, then we're solving for X. If they want the solubility of the ions in the solution, then you're going to plug that value back into the bottom part of the ice table, and we'll look at that in just a second. Okay, so when you do these, the first thing you want to do is set up or write out the dissociation. So this is my solid. So this is going to dissociate into Pb plus 2. And when you're doing these, basically if you remember, you can kind of uncross the charges. So these are going back to the ions they were before they formed a compound when you're dissociating them. If there is a subscript that goes to the front, because what that's telling me is there are 2 Cl minuses for every 1 Pb plus 2. Okay, so that's my dissociation. So then once I have that, I can set up my KSP. So KSP would be products over reactants raised to the power of the coefficient. This one is a solid, so that one doesn't get included. So then I would do Cl minus raised to the 2nd power. Okay, and that, like we said, I've said that a couple times, but that's the part you got to be the most careful with on these. Then what I can do here is I know what my KSP value is. Now, there's a couple different ways to do this. You could do these without doing the ICE table. I like to use the ICE table because that kind of ties it back to something we've done before and kind of gives us something familiar to use with this. But you'll be able to see once we go through a couple examples that if you don't want to use the ICE tables, you could do these without actually doing that. Okay, so if I'm going to use the ICE table, I have my PbCl2 goes to Pb plus 2, 2Cl minus. This is a solid, so that first column in these ICE tables is always going to be like we did with water before, where it's just a pure solid, so it's not going to change. And then what we're going to do is we're going to assume at the beginning these are 0. And then if we're solving for molar solubility, we're putting in x's. So this one is going to be plus x. This one is going to be plus 2x. And again, this is where you got to be careful, because before we didn't really have to worry about coefficients because most of those acid and base dissociations that we did didn't have coefficients. So then at equilibrium, I have x and I have 2x. Okay, so then these are the values that go into my KSP equation. So what I'll do is I'll substitute in KSP. So 1.7 times 10 to the negative 5th equals PB. So PB's coefficient is x. CL's variable is x. CL minuses is 2x. And this is why doing the ICE table helps you kind of keep that straight, and then not forgetting, again, to go and put back in that 2 there. So just slow down a little bit when you do these. Take a little more time to make sure you get all of those things substituted correctly, and then you don't forget any of those superscripts. Okay, so then this would be 1.17 times 10 to the negative 5th equals, and remember when this gets distributed to everything, so this is 4x squared times x is 4x to the 3rd. So then we're going to divide both sides by 4, and then we're going to do a cube root. So again, if you don't want to use, you can use your regular calculators on this, because we're doing this as a homework quiz and you're not taking it in class, it's open note. So that using your other calculator would probably be a little easier if you're doing cube roots. So take a cube root, and then x would be 0.0143 molar. Okay, so this is the answer to my question up here. So if it wants the molar solubility of lead 2 chloride, that would be 0.0143 molar. So another thing to remember is when you're reporting molar solubility, those have to have a unit. Those are going to have the molarity unit. Now, if they were asking for what is the concentration or the molar concentration of the different ions in solution, then you would plug that value back into what was at the equilibrium value of the ICE table. So this is still an ICE table like we've used before. So on this one, even though this question doesn't ask that, let's say it wanted to know what's the concentration of Pb plus 2, that would be equal to x. So that would just be that 0.0143 molar. If I wanted the concentration of Cl minus, that is, if I look at equilibrium, that's equal to 2x. So I would have to take this 0.0143 times 2, and then that would be my value there. And I don't have that calculated, but that would be the value there. Okay, any questions on that one? All right, so then the other type that we're going to look at is if they give you the molar solubility, what is the KSP? So this is the other variation of this. So again, remembering that molar solubility is x. So that means for this one, x equals 1.4 times 10 to the negative 2. I'm going to start this one the same way. So I have Ag2SO4, and I'm going to dissociate it. So there's 2 Ag pluses and 1 SO4 minus 2, and they're just breaking back up, going back to the ions they were before they became a compound. I can set up my KSP. So KSP would be Ag plus raised to the second power SO4 minus 2. Okay, so then since I have this right here, I'm going to go ahead and make this my ice table. So these I don't need. I'm going to assume that these are 0 to start out with. And then, like I said, because this is X, this value here, this would be, and I'm gonna do this a couple different ways. I'm gonna get rid of the variables because I really don't need the variables on this one, but I'm gonna put them in first so you can see where I'm getting these numbers. So this, if we had done this before, this would be like 2x, this would be x. So what I'm gonna do then, if I know this is x, I know that's gonna be my concentration of the SO4 minus 2. So I'm gonna put that in as 1.4 times 10 to the negative 2. This value here is 2x. So I have to double this before I put it into this box here. So this ends up being 0.028. So all I did was I took this 1.4 times 10 to the negative 2 times 2, and that's because that has that coefficient of 2. So that's why we had to double that. This one, you could leave it as it was because that one has a coefficient of 1. Okay, so then carry those down. 0.028, this is 1.4 times 10 to the negative 2. Then I'm going to plug those into my equation over here. So this is 0.028 squared times 1.4 times 10 to the negative 2. And then that gives me a KSP of 1.1 times 10 to the negative 5th. And then your KSPs, you won't have to put units on. Okay, so again, you could do this without setting up that ice table. I just like using the ice table because that kind of helps us keep track of coefficients. So again, remembering molar solubility is X. The X relates to the ions by their coefficients. So the coefficients come from how it dissociates. Then you plug those into your KSP, and then you can get your KSP from there. All right, any questions on either one of those two? And these just take a little bit of practice. Once you practice them, they shouldn't be, they'll get easier as you do practice with them. Okay, so then the last couple things is relative solubility. So molar solubility, like if you look at KSP versus solubility, it's not really the same thing. So you can't say just because it has a really low KSP means it does have a low solubility, but you can't just compare that one factor if you're comparing different things, because you have to look at the stoichiometry or the ratio of the ions in that solution. So like an example here is if you have MgOH2, the KSP is to the negative 13th, but the solubility is to the negative 5th. Whereas this iron carbonate has a KSP to the negative 11th, but its solubility is actually less. So you can't just look at a KSP value to say, yes, this one is more or less soluble than the other one, because you have to take into account, like this one is a 1-to-2 ratio of those, where this is a 1-to-1 ratio. So that's a little bit different than before, where we were looking at KAs and KBs when we were comparing dissociation. For the KSP, you have to consider both of those. You can't just look at the KSP. You won't have to worry about that because I'm not going to ask you specific questions about that on the quiz, but just to kind of keep that in mind. Okay, last thing we want to look at is something called common ion effect. Just like when we talked about this before, if you have a common ion in solution, it's going to affect the dissociation. So if you dissolve something in pure water, there's no common ion. So there's nothing that's going to prohibit it from completely dissociating, or not completely dissociating, but dissociating as best it can. If you try to dissolve it into a solution that contains a common ion, you think back to like Le Chatelier's principle, if there's already an ion in solution, it's going to shift that equilibrium back to the left, which goes back to the solid side, which would decrease the solubility. So if you have an ionic compound, the solubility of it is going to be lower in a solution that has a common ion. So if we look at the example here, if I'm trying to get calcium fluoride to dissolve, if I put this in pure water, then there's nothing in there to start with, so it can completely dissociate into the Ca, or not completely dissociate. These don't completely dissociate, but dissociate as best it can to Ca plus and F minus. But if I have a solution over here that already has F minus in it, and then I try to get that calcium fluoride to dissolve, this F minus is going to shift it back to the left. So not as much calcium fluoride is going to dissolve in this solution as I could get to dissolve in pure water. Okay, and that again ties back to that Le Chatelier's principle, where if there's already something in solution that it has in common, it's going to cause it to shift back to the side where it's less dissolved. So that's the last type of calculation. And this is similar to the first one we did. The only difference is instead of starting with the 0 and the 0 in the ice table, you'll start with an amount in one of those product sides of the ice table. So again, molar solubility means I'm solving for X for the compound in the solution that already has 0.1 molar NaF. So what I care about from this NaF over here is which ion does it have in common. So all I care about is the F here. The sodium's not going to affect anything because that's not common, but because it has this F minus in it, that is going to affect how much of this I can dissolve. So on this one, you would also need the KSP. So this is 1.46 times 10 to the negative 10th. And I'm going to do the same thing on this one that I did with the other one. So I'm going to start by setting up the dissociation. So Ca plus 2 to F minus. I'm going to set up my KSP expression. Ca plus 2, F minus 2. Then I'm going to look at my ice table. Don't need these. So on this one, there's no common ion for calcium, but this is where this is important. So this is going to be 0.1 molar. Again, we're using the ice tables. These are back to the ice tables. So these are going to be in molarity or big moles, whereas the BCA tables we were talking about yesterday, those are little moles. Okay, so then this is going to be minus X, because there's only one of those, or I'm sorry, plus X. This is going to be plus 2X, because there's a coefficient of 2 there. So this is X, this is 0.1 plus 2X. Okay, just like before, we're going to assume X is small when we do our calculation here. And then we're going to plug these back into our KSP. So our KSP is 1.46 times 10 to the negative 10th equals calcium is X, F minus is 0.1, because we're going to ignore this because we're going to assume that's small, squared, that comes from there. And then we're solving for X, 1.46 times 10 to the negative 8th. And again, you can see why, even though that's 2X, that this is such a small number to the negative 8th, that would not make a difference if we subtracted or added that to the 0.1. Okay, so again, KSP of the whole compound, this would be, or I'm sorry, the molar solubility of the whole compound. So molar solubility would be 1.46 times 10 to the negative 8th. Again, molar solubility has to have a unit on it, so we would put that molar on it. If it wanted to know what the concentration of the ions are, then you would take them back and plug them in over here. Okay, so those are the types of calculations you'll have to do with KSP. And like I said, it's just going to take a little bit of practice, getting used to the coefficients, getting used to solving for what they're asking for. And I'll post some, I redid the practice. That's why the practice isn't there yet, because I looked at it. I thought I had one, but it wasn't the best. So I made another one, and I'll put that up in a couple minutes after we get through here. But it follows a very strict pattern. If it's asking for molar solubility, you're solving for X. If it gives you molar solubility, you're solving for KSP. Okay, any questions on any of those calculations? Okay, the last little thing here that we're going to talk about, you won't have to do any problems with this, but this is just something to realize that there is an effect. pH of the solution can have an effect on solubility. So you can predict that. We're not going to do problems with this, but there are some substances that actually do dissolve better if they are in an acidic solution or a basic solution. So if you have an ionic compound that has a strongly basic or a weakly basic anion, that's going to increase with increasing acidity or decreasing pH. So there's some stuff like we didn't
You can drive it if you want.
Where we had to do this, but there are some compounds that dissolve better if you have an acidic solution. So that's really all you have to know about that. I'm not going to ask you any questions about that because the quiz is just going to be problems, but that's just something to keep in mind, that water is not always the best solvent for everything. Okay, questions from today or anything else?
I had a question about the lab. Would you be able to go over number 4?
Sure. Okay, so that one, so I don't have a printout of the lab. Was that the, was that one of them where you had to calculate the concentration?
Yeah.
Okay, let me get this here. All right, let me get a blank slide here. Okay, so when you're doing those problems for the lab, what those are asking for is to solve for the concentration. So those last 2 questions in the lab wanted to know what is the concentration of the acid. So if you look at the information that you have, like we talked about yesterday, if they want the concentration of acid or if they're asking for volume, we're going to use solution stoichiometry. Okay, so we're going to look at the information we have. So we knew that we had a volume of NaOH that was used to reach the equivalence point. So that was a value you had. Then you also knew the molarity of the NaOH that you used. Okay, the other piece of information you had was you had the volume of acid that you started with. So that was the acid that was in the flask to begin with. So when you're trying to decide how to set up that solution stoichiometry, you're going to start with the one that you have more, the volume of the one you have more information about. So on this one, I have volume of NaOH and I have a molarity of NaOH. So what that means is I'm going to start with the volume of NaOH. So whatever that is, that's going to go here. Okay, so this is going to be volume of NaOH that was needed to reach the equivalence point. So like when you were dropping that acid into the base, wherever you stopped, the final volume when it turned that light pink color. Okay, so that would go here. Just make sure it's in liters. So you want to convert it to liters first, and you can leave that as part of your calculation if you want. Then in your next bracket, this is where your molarity of NaOH would go. Okay, so molarity of NaOH, I think the molarity was 1, correct?
Yeah.
Okay, so 1 mole per liter, that was my molarity. I'm going to change this so it doesn't look like moles. So my big M of NaOH. Then my next column is going to be the ratio of acid to base. To get that, you have to do the balanced equation. So for that first one, it was NaOH plus acetic acid gives me NaC2H3O2 plus H2O. So when I balance that equation, that's a 1-to-1 ratio. So 1 mole of acetic acid to 1 mole of NaOH. So then what that's going to give me, and I'm actually going to get rid of this last bracket here. That's going to give me moles of acid in the beaker. So that's how many moles of acid are in that beaker to start with. So now this is where I need that other piece of information. I have a volume of acid that I started with, and I think that was 100 milliliters, right? Which is 0.1 liter. So once I solve for moles of acid, I want my concentration. Concentration is molarity, which is moles per liter. So I have moles of acid, and I'm going to put my liters of acid on the bottom. And then that's going to give me molarity for my unknown. So that's how both of those are going to work. So you'll start with the volume of NaOH it took to get to the equivalence point. Use the molarity of NaOH to get rid of liters, get it to moles. Use the ratio from the equation to get to moles of acid, then divide by your original volume of acid you started with. So one question I had from a couple people yesterday for this is when you're doing solution stoichiometry, you don't add volumes together. So this, because we're just talking about moles of acid, this is just the amount that you started with. The only time you would add volumes together would be if you're doing those BCA tables and you're taking those back to concentrations there. So if you're doing solution stoichiometry, you're never adding those volumes together. BCA tables is where you add the volumes together. On this one, and I know I've talked about this before, but I kind of recommend against it. But this one, you could actually do M1V1 equals M2V2 because this is a 1-to-1 ratio. The second one that you did in the lab where you're using H2SO4, that's not going to be a 1-to-1 ratio. Sure, I would just do the solution stoichiometry. But on this one, you could take your starting molarity, your starting volume, so that would be this, your volume of acid, which would be this, and then solve for your M. But that doesn't, it's a little bit trickier to use that M1V1 if you have a ratio that's not 1-to-1. So I would always default to the stoichiometry if you're doing ones that are not 1-to-1.
Okay, thank you.
All right, any other questions about that? And if you, I'll start going through those labs today or whenever you get those labs turned in. If you want, I can turn those back to you if you want to fix them. If you did something and you don't feel like you did it this way, I can give those back and you can fix them and turn them back in. All right, any other questions? Okay, so you've got Thursday and Friday this week to do some practice. So tomorrow is kind of continuation of today, so that'll give you some time to catch up with practice problems, the online problems. Friday, I will post, and if I get it done before then, I'll post it before then, but I have something that we use for this unit called a calculation review. So it's kind of a one-page first that says, okay, here's this type of problem, here's how you would deal with the calculations, here's this type of problem, here's how you would deal with those, and then some practice that goes with those. And then I have a video of me working through some examples of those that I can post as well. It won't be, I'm gonna modify it because obviously we're not doing all the calculations. I'm not gonna go back and test you over buffers because that was something we did before. So like I said before, the only two concepts you need to worry about on that final homework quiz on Monday are going to be titrations and then this solution or solubility KSP stuff that we did today. Okay, if you decide you want more practice or you want to see some problems worked out, let me know in the next couple days. If you want to have another meeting Friday just for review stuff, we can. If not, we'll plan on meeting at 9:30 on Monday morning to do a review of the concepts that'll be on the quiz. After that, I'll open the quiz up. It'll be open for the day. You can take it like a partner quiz if you want, and then turn that in, and then that'll be your last assignment. And then Tuesday, 9:30, if you'll hop on real quick, turn your cameras on if you're willing to do that, and we'll take a Zoom picture, and that'll be your last day. Any questions? Okay, I will see you guys later on. Let me know if you have questions.